Hi all, welcome back to this next iteration of physics lectures. And today we're going to spend some time talking about this mathematical concept called vectors. And this will be the subject of at least this video and another one, probably two videos just to break it up and make sure that we're all on the same page. So the first thing to talk about is this comes in handy. It's a word of encouragement. I know it seems kind of goofy to have it right now, especially because we won't be using it for a chapter or two, but I really do appreciate the idea of introducing something first and then giving you multiple exposures to it. So we'll see this again when we're talking about 2D motion, then acceleration, forces, momentum, all of these different concepts. These don't go away. So that's the first rationale for presenting it now. The second one would be is that it takes a long time to get comfortable with these. If I want to be perfectly honest, it took me several years, if not until I was halfway through my junior year, probably even later than that, to really kind of get a grasp of being comfortable. Part of this, the vector stuff, is just to make your life easier. It's a fast notation that can be used, and it will simplify some of your calculations once you trust the algebraic procedures established. So once you kind of understand what you're doing and know that it works every time, then you can kind of stop thinking about these vectors and start running the algebra again. So let's get at this. The first thing we need to talk about is, well, what is a vector? And from a graphical standpoint, a vector is a quantity that gives you both a what we call a magnitude, so a value, a number of some sort, but also a direction. And how we do this graphically is we represent a vector with an arrow. So the length of the arrow is indicative of the value of the quantity. And then the direction is just simply, we simply put an arrowhead on it. So there we go. So there's two pieces of information conveyed by this simple graphical picture. We have a magnitude, or a length if you would prefer, magnitude, and we have a direction. You hopefully see already how this...
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
You hopefully see already how this differs from some of your other numbers that you've dealt with before. So if you just need a number, that's what we actually call a scalar. And things like temperature, sure, or mass, these are scalars. There's one number, there's no direction associated with them, that's it. Whereas, for example, and I've already given you a list, if you're after some vectors, then you have things like force. It's not only how strong are you being pushed or pulled, but which direction are you being pushed or pulled. Or for example, something like velocity, how fast you're moving and in what direction. So that's why these vectors actually come into play, is because they're actually useful and they help us do some stuff. Now from a graphical standpoint, we said length of an arrow, you put an arrowhead on it, that indicates the direction, and you're done. One of the things that we should also mention is, how do you know if a vector is the same? And one of the nice things about vectors is that you can actually translate them. In other words, I have a vector, I can shift it to a different location. This is still the same vector. It has the same length, it has the same direction, and so it's the same, regardless of where on the page I put this thing. So what I say here is that the translations are free. Okay, so that translations are free. You are allowed to take a vector, a graphical arrow, and translate it, shift it anywhere that you want for convenience. Now I say that is opposed to rotations. Rotations are not free. are a no-no. Don't do it. Big. In fact, I'll put a frowny face here. Okay? Because when you rotate a vector, say you rotate a vector, those two vectors are no longer the same. You cannot get this vector, the one that I initially drew, to overlap perfectly with that one, no matter how you translate it. So these are not the same vector. That's kind of more of a fast and dirty way of thinking about it is, hey, if you can translate one vector and get it to lie perfectly on top of the other, then those two are the same vector. So that's kind of the graphical interpretation arrow. How about algebraically? So let's get an idea about, this is graphical. How do we do this algebraically? And one of the first things that we have to do when we're dealing with a vector is if we have a vector that we want to see here. Oops, let's get rid of that. If we have a vector and we had that vector, had that vector A here, it's always nice to draw a straight line if you can. There we go. If you have this vector A here, we'll just call this vector A. Okay. How can we possibly write vector A in terms of numbers? Okay. And the first thing that we have to do before we can do anything is take A, and we need to introduce a coordinate system. So we have something like, we have a coordinate system. Let's go ahead and draw that out. So here's a coordinate system, nice straight lines. And we say, okay, well, we'll call this the y direction. We'll call this the x direction. And we'll put some tick marks on it. We'll go 1, 2, 3, 4, 9. And we'll put some tick marks on this. And what this is really doing is this will allow us to take our geometric vector, our vector A here, and actually make it so that we can assign numbers to it. So what we're going to do, let's take A, and we already said, hey, translations are free. Let's go ahead and translate it. So what we're going to do is, if I can, we're going to translate it right here onto our coordinate axes. Awesome. Now we have vector A on coordinate axes. And now what we do is we simply count out. Let's count out how many in the x direction, how many in the y direction. We go 1, 2, 3. It looks about 2, 4, 6. It looks about 6 in the x direction right here. Right here. 1, 2, 3, 4, 5, 6. About 6 in the y direction. I'll be darned. That's pretty good. So now we have our vector on our coordinate axes. We know it points 6 in the x direction. We know it points 6 in the y direction. So if we had our we want to write this out, we could say something like, okay, well, vector A, or even better, A with the arrow over it, it's 6 in x direction, and 6 in y direction. Okay. And technically, this is it. You're good. This is all you have to do. Now, from a professional standpoint, physicists, mathematicians, we are completely lazy. We don't want to have to write all of this out. And so that we have some standardized notation that allows us to write this in a more compact form. And what that standardized notation is, well, you're probably familiar already with triplets. So for example, you're probably familiar if I did this 6, 6, 0, you would recognize that this is a point in space. It's a point in space located at 6 in the x direction, 6 in the y direction, and 0. Now I'll say, notice the parentheses, the rounded brackets. I said this is a point in space. If we want to represent a vector which goes from the origin to that point in space, we do the same kind of thing. We put 6 in for the x direction. We put 6 in for the y direction. We'll put 0 in. But so that we don't confuse it with the physical point in space, so that we know it's a vector pointing from the origin to 6, 6, 6, we don't use these rounded brackets. We use square brackets. And there we go. So this is vector A, which points from the origin to 6, 6, 0, and this is how we would express it algebraically. Now I have seen in some books where instead of using the square brackets, you'd use pointed brackets. So this is a different way that I have seen vectors represented. Your book uses the square brackets, so I'll try to do that as much as possible. The last one I'll say is sometimes this is probably the most compact that you can write it. Sometimes if you want, you can write it if you don't remember, say you're bad at remembering which one comes first. You could also write it as what we call unit vector notation or hat notation, where it's 6 in the x direction, and so we don't confuse this with a variable. We put a hat over it. Hats are very special. Plus 6 in the y direction. This has the same connotation. All three of these are the same. I guess I should put a equals here. A equals. All three of these representations are the same. They indicate 6 in the x direction, 6 in the y direction, none in the z direction. Okay. This is a way of algebraically representing it. A different way of doing it is to give a magnitude and a direction. Because we said, hey, vectors convey two pieces of information. Those two pieces of information are how long the arrow is and in which direction it points. So I'll go ahead and get rid of this for a moment, and let's see if we can figure out how to get the magnitude, the length of the arrow, and the direction of the arrow. So we have two things that we want here. Let's get rid of that. We want the magnitude, the length of the arrow, and the direction. And hopefully you can see already, I left it up here for a reason. Hopefully you see already the way of actually getting those two pieces of information, the length of the arrow and the direction that the arrow is pointing. We'll start off with the length here, and I'll use this fancy little thing. I'll highlight this and say, ooh, a nice fuchsia, just so we can see it. You see here that I have, if I go in the 6 in the x direction, then I go up into the y direction, I can actually form a nifty little triangle there. And even further, it's a right triangle, right? This is a 90-degree angle right here. So that will help us out. And the question is, if you know the length of the two sides of a right triangle, can you find the hypotenuse? Survey says, absolutely. That's something that we know as c squared is equal to a squared plus b squared. In other words, the Pythagorean theorem. I am not going to bother trying to spell it. I'll put Pythag. I guess Orion. Okay, so I will attempt to spell it. Pythagorean theorem. Okay. For a right triangle, this is the relationship between the legs, this length of the legs, and the hypotenuse. So here we see that the overall length of the vector is the hypotenuse of the triangle. And so we can say that the magnitude is 6 squared plus 6 squared. Or take your pick, I guess I'll call it 6 root 2. 6 root 2 is the magnitude. Now how do we actually represent the magnitude? This is a notation issue. If I call this vector A, how I would prefer to see you represent the magnitude is you write down vector A. So you say, okay, Greg, when you do this, you're telling me, okay, it is a vector. I know that. And to indicate the magnitude, we put it in absolute values. So this is the best notation for indicating the magnitude of a vector. Okay. Some older books will use a different notation. They will say, hey, if you have a vector A, then the magnitude of A is just simply represented by this. A with no vector over it. And you can see already that kind of gets confusing. Well, is A a vector and you forgot to write the vector sign? Are you talking about a magnitude of a vector, or is A just some scalar quantity? I do not like this notation. I do not encourage you to get into that notation. This is the notation that you should use if you want to be absolutely clear about what you're talking about. Okay? As for the direction, hopefully you can also see if I call this angle theta right in here, there are spiffy little functions that allow you to express the length of the sides in terms of, or the angle in terms of the length of the sides. In fact, if you're sitting there, you're racking your brain, say trig functions, you go, oh yeah, of course, there's that SOHCAHTOA thing. So, well, gee, it doesn't help if I, okay, let's make that an H. There's an H. Okay. SOHCAHTOA. Right, and if you've never heard that mnemonic, go back, look it up. But it's sine, opposite, adjacent, or hypotenuse, excuse me, cosine, adjacent, hypotenuse, tangent, opposite, adjacent. So in this situation, we know the adjacent side, we know the opposite side. And so we could write something like tangent of theta is equal to 6/6. Or theta is equal to the inverse tangent of 1. Now you should probably have that memorized already in your head. You should know what the inverse tangent of 1 is, because this is one of the special cases. You can plug it in your calculator right now, but you should know this like this off the top of your head right away. This is theta is equal to 45 degrees. 45 degrees. You say, well, I plugged it in my calculator and I didn't get 45 degrees. You have to double check. Okay, maybe your calculator is set in radians, and I believe this is something like 0.707 radians. Okay. So if you didn't get 45, if you got like this 0.707, then you're in radians rather than degrees. That's fine. You can give me an answer in radians if the question asks for it. If you give it to me on an exam, radians are fine, but you have to put the unit in there. You have to let me know which unit you're using. Homework, I believe that it will specify degrees or radians. So it'll tell you which unit it wants it in. And you're done. You notice now you've taken this vector. Let's summarize here. What you did was you drew a coordinate system. Then you translated the vector. Translate vector to the origin so that the tail's at origin, such that tail at origin. Then you simply count. You can then use the scale on the axis to count the vector. So use axis scale, and this allows you to write numbers for vector, and you're done. And then it's just a matter of, well, how is the vector supposed to be expressed? Do you need it in a triplet, or do you want it in magnitude and direction form? Those two formats convey the same information. So again, you have to look to see what the question is asking for. Now, the last thing I'll say is with the angle, notice, for example, this is 45 degrees above the x-axis, and that tends to be the standard. You measure angles with respect to the x-axis, and positive would mean that you're going in this direction, say counterclockwise. A negative angle would say that you're going clockwise. So positive angle is counterclockwise, negative angle is clockwise. And again, hopefully the homework assignments will indicate that. If there's ever a doubt, please feel free to email me. So where are we at the end here? Well, we've got a couple of, I'll summarize this here. So you've got a couple of different things floating around. First of all, you've got your geometric representation. So we're talking about vectors here. You have your geometric representation, where you're talking about a line with an arrow, so a magnitude and a direction. You have your algebraic representation, I'll put rep, where you're dealing with something like a triplet. Or maybe you're doing it in unit vector notation, so I'll call this, this could probably get me in trouble. I'll say x in the x-hat direction. You'll say some distance y in the y direction, some distance z in the z direction. Where those, again, are based on a coordinate axes that you have actually drawn. So these do not have any meaning unless you first do the coordinate axes. Coordinate axes. And the last thing is talking about how to take the algebraic representation and turning it into a magnitude direction. So if you have the algebraic representation, to get the magnitude, you apply something like Pythagorean theorem. Theorem. There we go. And if you need the direction, you're generally talking about a trig function. Trig function. Usually tangent. So I'll stop it there for right now. The next set of videos will be talking about algebraic manipulation, adding vectors, multiplying vectors, and I thank you for your attention. Have a good day.